All right. I'm pretty excited about what I'm doing today. I'm going to be doing some reading of this article. It's Oxidative Addition of Aryl Halides to Palladium Zero Complexes, a density functional study including solvation. I've got three colors of pens, so I like to take notes in different colors. I've got a cup with some coffee in it. Ah, that's delicious. And um, and there are lots of ways to read articles. Um, but I think one way to do it is just start at the beginning. Another way to do it is to read the abstract, start looking at the different figures, um, and um, and I think today what we're going to do is we're just going to start with the um, the abstract and then head to the introduction and see how far we get during this video. Um, so we already read the title. Now, as far as the abstract goes, we've got using density functional theory, which we usually abbreviate DFT, calculations in combination with an electrostatic continuum solvation model. All right, so I don't know what that is. We have investigated the oxidative addition of phenyl halides, PHX, to palladium zero complexes of bidentate phosphanes, where they're calling the bidentate. So bidentate, I know what that means. That means two bites, and phosphanes means that it's going to be doing, I guess each of those P's is going to be biting onto the palladium as ligands, yielding aryl halo complexes, PP, PD, PHX, where the phenyl halide, each of them, right, is a different ligand as well, with X equals chlorine, bromine, and iodine, and PP equals 1,2-bis dimethylphosphenoethane, or this long word. Oh, those are different choices. Those are not the same thing. So PP, okay. So PP can be two different things. Dimethylphosphenoethane, or P22-bis dimethylphospheno 1,1-biphenyl. Biphenyl is something that um, I've seen before in liquid crystals, which is a whole another thing, but I do know what biphenyl is. I don't know what all these things are. We have considered the formation of the reactive 14 electron species from the saturated PDPP2, as well as different pre-reaction complexes with an intact phenyl halide. We find that ligand dissociation is the limiting reaction step. So ligand dissociation is the limiting reaction step. And so limiting steps are going to be the highest activation energies. While the formation of the pre-reaction complex and the oxidative addition itself are energetically very favorable. So the formation of the pre-reaction complex, which probably has all the things together, and the oxidative addition itself are energetically favorable or very favorable. Okay. The concerted transition state for oxidative addition, known in the gas phase, could not be found in solution. The concerted transition state could not be found in solution, so with a solvent. Instead, we propose a pathway involving the very facile dissociation of the halide from the pre-reaction complex with subsequent collapse to the products. All right. So some of those words I know. Propose a pathway involving the very facile dissociation. Okay. Very interesting. All right. So then let's continue with the introduction. The oxidative addition of aryl halides to palladium 0D10 complexes, forming palladium 2 aryl halo complexes. All right, palladium 0 with M number of ligands attached, plus aryl halide goes to something with all of them attached in a +2 state. So the 0 is the oxidation state. AR denoting aryl throughout the paper is a fundamental reaction in organometallic chemistry. Woohoo! It constitutes an elementary step in the catodic cycle of a series of important palladium catalyzed reactions that transfer an aryl group onto a variety of substrates. These arylation reactions include the formation of arylamines, aryl ethers, and aryl thioethers from amines. Wow, look at all these different references. So this is important. um, Alkoxides and sulfides, respectively, of alkenyl arenes from alkenes. There's the Heck reaction of biaryls and alkylarenes from organoborane reagents, Suzuki coupling, and of biaryls as well as alkenyl and alkynyl arenes from magnesium, aluminum, zinc, tin, or zirconium organelles. So still Negishi and related cross couplings. All right, so again, and we've just talked about the type of reaction and how important it is to all of these different named reactions, some of which I've actually heard of before, though I do not know exactly what they are. I know a little bit more about what they are because it tells me. So for example, a Heck reaction must be of alkenyl arenes from alkenes. Okay, well, lots to learn. In all these cases, the electrophilic aryl halide, so electrophilic aryl halide, so full of electrons, electron loving, so that must be positive. Okay, is right. Let's see. So, wait a minute. Okay. Yeah, no, I don't know what I was going to say there. Is oxidatively added to a palladium 0 complex before being transferred onto the other coupling partner. The aryl halide oxidative addition can even constitute the rate limiting step of the process. The right. So this can be rate limiting, the oxidative addition. Okay. And so I think oxidative addition is one step in a process of a reaction, because then, if I understand from what I've been doing so far, so once it's attached, so the oxidative addition is going to connect the aryl halide to the palladium, and the palladium becomes a palladium 2, palladium 2. All right. So palladium 0 complex is going to have a couple ligands on it, 2 ligands here to be specific. And after that, there's going to be 2 more ligands attached because the aryl group and the halogen group are going to be, so it's going to go into 4 ligands in a +2 state. Okay. A number of experimental studies have provided insight into mechanistic aspects of the reaction, in particular with palladium 0 phosphane complexes. Wow, that's a lot. Only a few of them, however, have been concerned specifically with complexes of chelating diphosphanes. So, although this class of ligands is widely used. So chelating, I think, means more than one bite. So bidentate, tetradentate. From these studies, we highlight some of the mechanistic features that have emerged. One, oxidative addition occurs to a coordinatively unsaturated complex. In the case of highly sterically demanding monodentate phosphanes, such as P, O-tol-3 or PT-butyl 3, even monoligated 12 electron species are involved. All right, so we've got 12 electron species. We've got 14 electron species, so 14 electrons, 12 electrons. And so this is a monodentate phosphane ligand. And so orthotoluene versus PT-butyl with three of them in each case. Right, so there's lots of things. All right, so in my head, we've got P with a couple of electrons here, and then we're going to put 1, 2, 3 T-butyls, tertiary butyls. So 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So yeah, so very sterically hindered. I think the toluene, all right, you're testing me here, or I'm testing myself. Let's see, so I'm going to put a P with a pair of electrons there, and then ortho, I would guess. So let's see, 1. Toluene, I think, has an alcohol on the other side. No, a methyl. Well, I don't know which. Oh, it's got, so yeah, I think it's got to be a methyl. Toluene, oh, phenol. Yes, phenol would have it on the other side. So toluene's got to have a methyl group. Has been a while since I've done OChem. And so very sterically hindered, monodentate, because there's one pair of electrons that are going to form the coordinate covalent bond with the palladium. All right. Highly, so in the case of let's get on screen here. Highly sterically demanding monodentate phosphane. So these are phosphanes. Even monoligated 12 electron species are involved. So 12 electron, 14 electron. All right, I have to think about what that actually means as far as what are these electrons? So which 12, which 14? I'm thinking about, no, well, so I'm thinking about the palladium, and the palladium has 10 electrons in the D subshell. So, right, because it's a D10 complex when it's palladium 0. Anyway, we'll put our Gen Chem knowledge together with this sometime. All right, so just to finish this off, ligand dissociation is therefore always a preparatory step for oxidative addition and may even be rate limiting. For bidentate phosphanes, the only, or at least most reactive species undergoing oxidative addition is palladium PP, where PP equals chelating diphosphane ligand. All right. Oh, so this is what we're learning from all these other studies, because it says 1, oxidative addition occurs in a coordinatively unsaturated complex. In the case of highly 12 electron species involved. Ligand dissociation is therefore always a preparatory step for oxidative addition. Let me go back and underline ligand dissociation. So ligand dissociation means it must leave. So which ligand leaves? I guess we'll have to figure that out. 2, for bidentate phosphanes, the only, or at least most reactive species undergoing oxidative addition is PP. Certainly in the absence of ligands with good pi acceptor properties, such as methyl acrylate. Most reactive, the only or most reactive species. Ligands with good pi receptor properties. Recently, Blackmond, Buchwald, and coworkers presented evidence for the case of the PD binap catalyzed, binap equals 2,2-bis diphenylphosphino 1,1-B-naphthyl, like the PHTH in phenolphthalein. Amination of bromobenzene, where the oxidative addition actually occurs to the amine complex, blah, 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 when the amine is present in excess relative to the aryl halide. All right. Keep going. The available kinetic data do not allow one to exclude the formation of a pre-reaction complex, all right, after full dissociation of the first PP ligand. So pre-reaction complex after full dissociation of the first PP ligand. So ligand dissociation means the ligand leaves. One of them does, and then there's a complex. Such a species in which the ARX bond is still intact is likely to be involved at high ARX concentrations because there's a lot of it around. Okay. The coordination of a solvent molecule directly to the reacting complex can be excluded. Well, that's good because I think we're using a continuum model for the solvent, so we would not want to have actual, that's what we're doing, that's what they're doing. All right. And there's some references there for our light reading pleasure. There is no indication, evidence for paramagnetic species, sensitivity toward radical scavengers, formation of biaryl side products, etc., for the participation of radical species in the reaction. A single electron transfer mechanism is therefore unlikely, in contrast to the situation for aryl halide oxidative addition to nickel complexes. Woohoo! So nickel's quite different. We're doing palladium. And really, they're laying out all the steps probably for doing what they're doing, right? Because it was talking about a pre-reaction complex, and we saw that pre-reaction complex was noted in the abstract. A Hammett study, whatever that is, using a series of substituted aryl chlorides, okay, found a highly positive rho value and a strong correlation with Hammett's sigma minus constant, which suggests an SNAR type transition state with charge separation. There are so many words in that sentence that I do not understand. But let's see. So there's some constants. So the rho value, there's a sigma minus constant, and it suggests a nucleophilic substitution. It's not SN1, it's not SN2, it's SNAR, an aromatic nuclear substitution. Is that what that could be? All right, so SNAR, writes a question mark after it because we'll look that up, but Substitution nucleophilic seems familiar. On the theoretical side, carbon X oxidative addition. So does this always mean halide? I don't know. Has generally received much less attention than oxidative additions of relatively unpolar bonds such as HH, CC, or HCH. The addition of iodomethane to square planar rhodium-1 and iridium-1 D8 complexes has been investigated in the context of Monsanto-type carbonylation processes. The reactivity of three coordinate complexes of the same metals toward activation of the CX bond of fluoromethane and the tetrahalomethanes was also studied. All right, well, we'll come back to that because that's not palladium. The first study on CX oxidative addition of D10, all right, that's palladium, metal center was reported by Bickelhaupt et al., who investigated the addition of chloromethane to a bare palladium atom. Comparing conservative oxidative addition, SN2, substitution, and single electron transfer under Cl star asterisk abstraction, they found the concerted process to be the most favorable one. So this sounds like a DFT or a computational chemistry model. Accounting for salvation, water or diethyl ether, with a simple Born-Onsager model did not change the situation qualitatively. All right, we got to our first scheme, but we haven't referenced it in the paper yet. More recently, Diefenbach and Bickelhaupt emphasized, however, the quantitative importance of relativistic effects for this reaction. Only a few computational studies have been devoted to the oxidative addition of CX bonds to a D10 complex. Well, I think that's sort of what we're doing, or it's definitely related. All with palladium with two ligands. The halides and ligands involved were chloro and bromobenzene. L equals diaminocarbene. All right, no phosphorus there. Iodobenzene. Okay. Chloro and bromobenzene, which is exactly what we've been working on. L equals, so the ligand was diaminocarbene. Okay. Iodobenzene, where the ligand was 1,2-diphosphenoethane. I think diphosphenoethane is going to be this thing, diphosphenoethane with two carbons here and hydrogens in the other two positions. That seems like not sterically. Like, all right, so zoom in. So, right, so if your choice was we had a phosphorus with three T-butyl groups, that's going to be very crowded over here. This is two phosphoruses attached to two carbons. So with two carbons there, that's going to be pretty rigid. Like this thing stays out of the way of this entire side. And let's see, flatten that out a little bit. And all right, so we're going to get to this scheme eventually. So we're about to. So let's see. All right. The halides and ligands involved, blah, 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 and a series of substituted alkynyl, so that's triple bond halides, yep. And substitute fluorobenzenes. For iodobenzene, a concerted transition state, scheme 1, was found, in which the plane of the three reacting atoms, palladium, carbon, ipso and I. Ipso, well, anyway, I think it must be this carbon here. So yes. Oh, I think it's going to all say there. Oh, is it tetrahedral? Which the plane of the three reacting atoms is almost perpendicular to the palladium, the phosphorus, palladium, phosphorus coordination plane. The barrier relative to the free reactants was minus 16 kilojoules per mole, plus 16 kilojoules per mole relative to the N square. I'm not remembering what it's eta. I don't know what that is. Squared arene pre-reaction complex. In the case of fluorobenzene, the reaction was also concerted, but the reacting atoms lay in the coordination plane. All right, here's our scheme. So is that bonded there? All right, so let me back this up a bit. And let's see. Oh, two. Yeah, we're way down there. All right. So in the case of fluorobenzene, the reaction was also concerted, but the reacting atoms lay in the coordination plane, and the barrier relative to the free reactants was 172 kilojoules per mole. No pre-reaction complex could be located. Taking solvation water into account and using the Cosmo continuum solvation model, and we're interested in solvation models. Cosmo solvation model lowered the barrier by a few kilojoules per mole, but 172 kilojoules per mole is a huge barrier. Things aren't happening. Solvation lowered the barrier by a few kilojoules per mole. Okay, so with orthonitro-substituted fluorobenzenes, however, only the Zwitter ionic intermediate 2 was found in solution rather than a concerted transition state. 2 resembles the Meisenheimer intermediate of SNAR reactions, featuring a pyramidalized C-ipso atom. Its elongated carbon-fluorine bond suggests facile fluoride elimination, followed by collapse of the product. Facile means easy, and nothing about this seems easy. But I think we're getting to the end of the introduction at least, because it says in the present contribution, right? So they're talking about what they're doing, right? And next page is computational. So let's press onward, finish the introduction. In the present contribution, we have used density functional theory calculations to investigate the oxidative addition of chloro, bromo, and iodobenzene to complexes of palladium with the bidentate phosphane ligands, blah, 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 DMPE, and blah, 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 BIMEP, BMEP, and I don't know how you pronounce that first one, C scheme 2. We focus on the nature, which we'll do in a minute. We focus on the nature of the transition state, contrasting a concerted with an SN Aryl type process. In particular, we consider the influence of the moderately polar solvent tetrahydrofuran, THF, on the mechanism using the electrostatic continuum solvation model Cosmo, still. As illustrated in reference 40, alternative pathways can become available in solutions that are not viable in the gas phase. For instance, a charge-separated species such as 2, in scheme 2, is most unlikely to be competitive in the gas phase. We also examine the formation of the reactive 14-electron complexes 2 from the tetra coordinate 1, as well as different pre-reaction complexes 3 with an intact phenyl halide. All right, I think it's time to go look at this thing. All right, so here's this scheme of reactions considered a numbering scheme. All right, so DMPE, dimethyl phos. What's it called? Dimethyl 1,2-bis dimethyl phosphino. We're both phosphinos this time. Dimethyl phosphino. And what's that going to be? It's got some stereochemistry in it. They're both 1,2. One's 1,2-bis dimethyl phosphino. The other is P22-bis dimethyl phosphino 1,1-biphenyl. All right. So there's our biphenyl. There's our dimethyls. This has some shape to it. Huh. This one does not. All right. Well, and we've got the 2. All right. So, okay, this is interesting. I think anyway. So we've got 4 ligands attached here. We've got 2 bidentates. We take away a PP, one of them, and we're left with 1 ligand. And then we add the phenyl halide, and we get, right. Oh, and this is showing not square planar at all. This is showing perpendicular, tetrahedral-ish, no, 90 degrees. All right, and then we've got all right. So then what do we go to is maybe what we're asking here. And then we end up with square planar. So this is showing square planar down here. What's going on in between? And I mean, why in the world would, okay, I hope they address why this bidentate ligand is being removed. Because bidentate, well, from an entropy standpoint, so this, well, I have to remember my ligands now, but okay. And they're assuming, okay, they're going to look at this. And I think that's interesting. So just the X comes in, XPD, the carbon comes in closest, both of them come in, and the halogen comes in. So 3.1 ABX, 3.2 ABX, because we're doing both of these. So, okay, so what I know is, let's see this. Here's our starting point, so we're going to need to know the energy of this. We're going to remove a PP, a diphosphino in this case, but right, a bidentate. And then we're going to need to know the energy of this plus the PP, plus the phenyl halide. And then we're going to have to build complexes to see what the energies are of these. And all right, so now that we've seen the scheme, let's go read this again. All right, so in the present contribution, did I unplug anything? I did, but we have used density functional theory calculations to investigate the oxidative addition of chloro, bromo, and iodobenzene to complexes of palladium with the bidentate phosphane ligands. So they're phosphane ligands, but they're dimethylphosphino names. Phosphane ligands, all right. DMP and this, which is BMAP or BIMAP, I'm not sure which. We focus on the nature of the transition state. We like focusing on the nature of the transition state. Contrasting a concerted with an SNAR type process. In particular, we consider the influence of the moderately polar solvent THF on the mechanism using the electrostatic continuum solvation model COSMO. As illustrated in reference 40, alternative pathways can become available in solution that are not viable in the gas phase. For instance, a charge-separated species such as 2, and we're going to look at that, 2, 2, 2, oh, 2 charge-separated species. I'm assuming that's what it's talking about. Charge-separated species is most unlikely to be competitive in the gas phase because that's hard to separate charges when the dielectric constant is low. Finally, I think something I've got. But and this uses a moderately polar solvent. So we've got THF, and some of the things we've been doing have involved DMSO, dimethyl sulfoxide. So which is more polar? Dimethyl sulfoxide. Anyway, well, we'll figure that out. We also examined the formation of the reactive. Okay, so we still don't know what these 14 electron complexes. Two. Okay, so this is a 14 electron complex. Okay, so first gas here, palladium has 10 electrons. We bring in 2 ligands. Each of those has 2 electrons. So palladium has 10 plus 4. We'll put a question mark there, but that might be a 14 electron complex, but then a 12 electron complex. Well, still to be seen. But let's see. So, all right, what I love about this is somehow they've gotten to the point where they have well-identified things that they can model and calculate the energies of. And one of them, at least, looks like one of the things we've been looking at, which is a square planar with 2 phosphorus groups on one side and a phenol, which would be a benzene, and an X group. Which is a halogen. So, okay, maybe this is why this is one of our key references. Let's pick up in the next video on computational details. I'll go ahead and stop this now.